Hey everyone, in this video we're going to actually use the trigonometric identities that we learned in the last video and apply them to certain problems. So we'll start off by using the period identities, and we're going to use them to simplify the expression sine of 31 pi divided by 6. Now we want to express 31 pi over 6 as its reduced angle plus the full number of terms it took to get there. Using strategies from chapter 7, we can find that 31 pi over 6 is the same as 7 pi over 6 plus 4 pi. That 4 pi, of course, is 2 times 2 pi, and according to our identity, that 2 times 2 pi vanishes, leaving us with the expression sine of 7 pi over 6. So the conclusion is that sine of 31 pi over 6 is equal to the sine of 7 pi over 6. Now we'll do the same thing with the tangent of negative 17 pi divided by 6. When I look at the reduced angle of 17 pi over 6, I'm going to get pi over 6 minus 3 pi. Now remember that the tangent version of this period identity works just a little bit different. Since this is the tangent function, all multiples of pi vanish. So this is going to simplify to the tangent of pi over 6. So the conclusion is that the tangent of negative 17 pi over 6 is the same thing as the tangent of pi over 6. So when doing problems like this, remember that the functions sine, cosine, cosecant, and secant all have even multiples of pi vanishing, whereas the tangent and cotangent functions have any multiple of pi vanishing. Now let's move on to a new kind of problem. We want to prove that the cosine of theta plus the sine of theta times the tangent of theta is actually equal to the secant of theta. And what we're going to do is we're going to simplify the more complicated side of this identity, namely the cosine plus sine times tangent side. So to get our work started, we're going to write out the more complicated side and think about simplifying this expression. And we've got to start thinking about what trig identities are going to be useful here. The first one that stands out to me is transforming that tangent of theta using our quotient identity. So I'm going to rewrite this expression as the cosine of theta plus the sine of theta times the quotient sine of theta divided by the cosine of theta. I don't have anything canceling out yet, but I do have two expressions in this problem that I can try to combine. And by combining, I mean trying to find a common denominator so that I can combine or put together these two fractions into one. What I'm going to do is take that cosine of theta and multiply it by cosine of theta divided by cosine of theta. This will give both fractions a denominator of the cosine of theta, allowing me to add them together as cosine squared theta plus sine squared theta divided by cosine theta. So I don't see any algebraic simplifications happening because I don't have any common factors to try and cancel, but what I do see is cosine squared theta and sine squared theta. This tells me that I should be using my Pythagorean identity so that I can turn the numerator into the number 1. Now that I have the expression 1 over cosine of theta, I can use my reciprocal identity to turn this into the secant of theta, which is what I was trying to show all along. So pretty much any trig identity problem is going to have the following nature. I'm trying to show that both sides of the equation are equal to each other, and sometimes this means taking the more complicated side and simplifying it to look like the other side of the equation. And you can see that I've done this by a combination of trig identities and algebra. And since I was able to take the left-hand side and simplify it to make it look like the right-hand side of the original expression, I've been able to prove this identity. For our next example, we're going to prove that the cotangent of alpha plus the sine of alpha divided by 1 plus the cosine of alpha is equal to the cosecant of alpha. Now the use of alpha here is just to show you a different variable name, but each one of these identities works for any variable that you want. It's just a variable name or it's just a choice of symbol. But like before, I'm going to start with the more complicated looking side, the cotangent of alpha plus sine of alpha divided by 1 plus cosine of alpha. We're going to see that combining fractions will be a pretty common theme, but I first want to turn that cotangent of alpha into the cosine of alpha divided by the sine of alpha using our quotient identity. And even though I currently don't have common denominators, I can multiply each fraction by the correct term so that I do have common denominators. I'll multiply the first fraction by 1 plus cosine of alpha over 1 plus cosine of alpha, and then I'll multiply the second fraction by sine of alpha over sine of alpha. Unfortunately, the nature of these problems does mean that they get a little bit messy before they get pretty, so part of this is also an exercise in bookkeeping. But now that these fractions do have common denominators, I can go ahead and multiply them and add them together so that I get the cosine of alpha times 1 plus the cosine of alpha plus sine squared of alpha, all divided by sine of alpha times 1 plus cosine of alpha. So using some algebra, I have a little bit more simplification that I can do. I can distribute that alpha to get the following. Now for each step of simplification, I'm trying to see what kind of trig identities I can apply. But since I see a cosine squared and a sine squared being added together, This tells me that the Pythagorean identity again can be used. So I'm going to replace that entire numerator with the cosine of alpha plus 1 divided by the sine of alpha times 1 plus the cosine of alpha. So two nice things happened here. My numerator got a little bit nicer, and now I see a common factor of cosine of alpha plus 1. These two things are going to cancel out, giving me 1 divided by the sine of alpha, which is the same thing as the cosecant of alpha, and that's what I wanted to show. So because I was able to make the original left-hand side look like the cosecant of alpha, this proves the identity and we're done with the problem. And again, mostly this was a combination of using trig identities while also doing a lot of algebra and simplification and combining of fractions. So it's like we have a lot of chapter 1 material that's happening in the background. We're essentially looking at algebraic expressions and seeing how they simplify and how common terms in the numerator and denominator can cancel each other out. For our next example, we're going to prove that 2 times cosecant squared of x is equal to 1 divided by 1 minus cosine of x plus 1 divided by 1 plus cosine of x. And I promise you this was going to be a common theme. Our first step is going to be to take the right-hand side, being the more complicated of the two sides, and try to combine these fractions. Since they don't have common denominators, I need to multiply the first fraction by 1 plus cosine x divided by 1 plus cosine x, and then I'll multiply the second fraction by 1 minus cosine x divided by 1 minus cosine x. And so you see, I'm just multiplying each fraction by a term constructed from the other fraction's denominator, because this is going to give both fractions the same denominator of 1 minus cosine x times 1 plus cosine x. And now that the denominators are common, we can add the numerators, giving us the full fraction of 1 plus cosine x plus 1 minus cosine x divided by 1 minus cosine x times 1 plus cosine x. So you can already see that the challenge of this problem is that every term looks very similar. It's either a 1 minus cosine x, or a 1 plus cosine x. So the point of this problem is to give you some practice with some good bookkeeping and just overall trying to be careful with your organization, because it's very easy to write the wrong symbol and mess up the whole problem. I'm going to look at my numerator to see if anything additively cancels, because what I notice is that I have positive cosine of x and a negative cosine of x. Those are going to cancel out and give me a 2 as the numerator. My denominator can also be FOILed out to get 1 minus cosine squared of x. And already this fraction looks a lot nicer, but I still have a little bit of a ways to go to get the final result of 2 times cosecant squared of x. But because I see that 2 in the numerator, and I see a 2 in the original left-hand side, this tells me that I'm headed in the right direction. At least that coefficient of 2 is showing up, telling me that I am making my way towards the final answer of 2 times cosecant squared of x. But I don't really see how I can simplify this any further, at least algebraically. And right now, it's not overly clear what identity to use because I don't have an identity that explicitly represents 1 minus cosine squared of x. So the strategy that we're going to use in this video is going to show us how to take a known identity, namely one of our Pythagorean identities, and transform it to fit our situation. If I look at the symbols 1 minus cosine squared of x, I see that the Pythagorean identity sine squared of x plus cosine squared of x equals to 1 at least has some of the same characters, cosine squared of x and 1. But imagine taking this identity and subtracting cosine squared of x from both sides. What I would get is the new identity, sine squared of x equals to 1 minus cosine squared of x. And this is great news because now that I've transformed the Pythagorean identity into this new form, I can use it directly in our problem. This means that the original right-hand side of 1 divided by 1 minus cosine of x plus 1 divided by 1 plus cosine of x, which is equal to 2 divided by 1 minus cosine squared of x, can be transformed as 2 divided by sine squared of x using our manipulated Pythagorean identity. And finally, I can rewrite 2 divided by sine squared of x as 2 times the cosecant squared of x using our reciprocal identity. So the main takeaway from this example is the following. Sometimes I can't use identities exactly as they're presented either in these notes or in these videos. Sometimes I need to manipulate them just a little bit with a little bit of algebra so that they fit our situation. When I see the symbols 1 minus cosine squared of x, I know to look at one of my Pythagorean identities because I see the number 1 and I see a cosine squared of x. So my goal is to take the original Pythagorean identity and see if I can use some algebra to turn it into something more useful for our problem. For our next problem, we're going to prove that the tangent squared of x divided by 1 plus the secant of x is equal to 1 minus the cosine of x divided by cosine of x. And this is going to be a meet in the middle strategy, as I call it. Now, obviously this problem looks kind of daunting because I have two fractions with a lot of characters therein. And it doesn't look like either side can be thought of as the more complicated side because they're both kind of complicated in their own right. So when I see a problem like this, it's really a good idea to take both the left and the right hand side separately and see how they simplify. Because maybe the left hand side simplifies to something that the right hand side simplifies to in their own rights. And if that happens, if we can say they meet in the middle, we can prove the identity. So let's go ahead and take a separate look at the left hand side. That numerator has the character tangent squared of x, and manipulating one of our Pythagorean identities allows us to change the numerator into the secant squared of x minus 1. Even though I didn't actually put the work onto this slide, if you took the original Pythagorean identity that had the tangent function in it and solved for tangent squared of x, you would find it that is equal to secant squared of x minus 1. But now we'll see how we can do something kind of crafty with the numerator. I have secant squared of x minus 1, which is technically the secant squared of x minus 1 squared. I can use my difference of squares formula to factor the numerator as secant of x plus 1 times the secant of x minus 1. It turns out that using the difference of squares formula on our Pythagorean identity-like characters is going to be a pretty common strategy when you're doing these on your own. But the reason I wanted to do it here is because I'm seeing some similar characters in the numerator and denominator. The numerator is secant squared of x minus 1, and the denominator is 1 plus secant squared. So by factoring using my difference of squares formula, I see a common factor of secant of x plus 1, and this cancels out. Now I'm left with just the secant of x minus 1, so I'm going to stop here with the left-hand side and now look to the right-hand side. The right-hand side, which is 1 minus cosine of x divided by cosine of x, has a numerator fraction that allows me to split up this entire right-hand side as 1 divided by the cosine of x minus the cosine of x divided by the cosine of x. This is also a pretty common strategy when dealing with trig identity problems, taking a fraction and splitting it up using its numerator. But I can replace 1 divided by the cosine of x with secant of x, and the negative cosine of x divided by a cosine of x just turns into a negative 1. Now what we're seeing is that both the left-hand side and the right-hand side landed or simplified at the exact same place. So in this situation where the left and right-hand side simplify to the same expression, we get to say that the left-hand side and the right-hand side of the original equation are in fact equal to each other, and this proves the identity. What you're going to find when you're working your own problems is that not every trig identity problem is the same. Each one is going to be a little bit different, and it's possible that each one might take you more than one try to solve. When this happens, the whole point is not to get discouraged. The point is to try again or ask for help if you need, but just know each problem is going to be a little bit different, and in a sense you do have to play with them a little bit to figure them out. Alright, so we're going to conclude this video by showing you one more new type of problem known as the substitution problem. Suppose that we are given that the sine of theta is equal to x divided by 2, where theta is an angle between 0 and pi over 2. And when we say this, we simply are just saying that theta is an angle between 0 and 90 degrees. So we're just getting some bearing on where we are in the unit circle. For this problem, this just says that we're restricting our scope to the first quadrant. The goal of this problem is to take the radical expression, the square root of 4 minus x squared, and write it as a trigonometric expression using the given information. Our first step is to take the sine of theta equals to x divided by 2 and solve for x. This will give me that x is equal to 2 times sine of theta. Now the second step is going to be to make the substitution. I want to take my radical expression, square root of 4 minus x squared, and replace x with 2 times sine of theta. This gives me 4 minus 2 sine of theta squared, which simplifies into the square root of 4 minus 4 sine squared of theta. Next, I'm going to factor out that square root of 4, which is just 2, to give me 2 times the square root of 1 minus the sine of theta. Now, I can look at my 1 minus sine of theta and my Pythagorean identity and see that this will allow my expression to simplify as 2 times the square root of cosine squared of theta. Now, normally when I take the square root of something like this, I get a positive and negative solution, but we were told that theta lives in the first quadrant, between 0 and pi over 2 radians. And every angle, rather every coordinate in this quadrant has a positive x-coordinate. This allows me to take the square root of cosine squared theta and just write the whole expression as 2 times the cosine of theta. And again, I get the positive solution to this because of where theta is. Since theta corresponds to the first quadrant, this has to correspond to a positive x coordinate, meaning the cosine is a positive number. And this is going to complete the problem. If my angle theta was in the fourth quadrant, then my final answer would have been -2 times cosine of theta, because I would have gotten a negative value for my answer. Alright, well, thank you so much for watching. Please reach out to me with any questions you have, and have a great day.